All right, so part 2 of the section on trigonometry, or review on trigonometric functions. This is still the second part of 1.3, graphs of trig functions. And it's, their transformations, all right? So we'll stick to the most basic of the functions, sine of x. And of course, if you take a full trigonometry class, you will learn all sorts of, things like what does the secant function look like and the inverse sine function look like and all that. We will not go into all the details. We'll just consider the basic functions here, all right? And let me just try to sketch the plane, the axis, all right? And because that would make it a little easier for us to graph them and save some time. Okay, so we'll start with sine and then cosine and then the tangent. Okay, so sine function, remember it starts at 0. And I know you have seen these, so I'm going to sketch them quickly. The thing to remember here is, let's call this pi, and let's call this 2 pi. It's periodic with a period of 2 pi. The highest point is 1, which is attained when the angle is pi over 2, sine becomes its highest, right, which is 1. So this is called the maximum, technically absolute maximum, also a relative or local maximum. And then by the time you get the angle gets to pi, of course, it backs the y value, the sine of x goes down to 0, and then 3 pi over 2, which is the bottom of the unit circle, it becomes -1 and gets back in here. Right. What I have drawn here is one complete cycle, right? And this is from 0 to pi over 2 is called the fundamental region of, or the fundamental domain of sine of x. And what you do is you just kind of keep repeating this. And so if this continues on forever, of course, like the sine wave. All right, but this part here, okay, this is called, like I said, this is called the fundamental period. Okay. And you can talk about things like the amplitude, which is 1, the period is 2 pi, and so on. Okay, cosine of x starts at 1. When x is 0, y is 1. Cosine of 0 is 1. And again, let's say that if this is pi, remember pi over 2, cosine hits 0 at 90 degrees, and then goes down to -1, and goes back to 0. And by the time you get to 2 pi, of course, it starts at the same point, which is the value of 1. And of course, you can continue this and so on. But again, the fundamental region here, or the fundamental domain, is from 0 to 2 pi. Everything that happens with the cosine has already happened between 0 and 2 pi, right? Going down, all the way down to -1, going up to 0, and then going up to 1. Okay, tangent, very, very different, right? Because it is it's actually a ratio of sine and cosine. As we denoted, let's call this pi, at pi over 2, which is 90 degrees. Well, okay, pi over 4, the value is 1. And then it just keeps going up to infinity. And right at pi over 2, you remember what happens? The tangent value is undefined at pi over 2 and -pi over 2. So you have these asymptotes. And in fact, you have infinitely many asymptotes happening every pi radians. Okay, so you may want to just draw a bunch of these horizontal dotted lines. And then remember at pi, the value is 0. And so what's going to happen as x goes from like 0 to pi over 2, tangent goes up to positive infinity. And right at pi over 2, tangent vanishes. It's not defined. But as soon as you pass pi over 2, even just a little bit, pi over 2 plus 0.000001, it comes back from the negative end of the Earth. So it's almost like this positive infinity is connected to the negative infinity and comes back from the negative side. You keep looking up, say, hey, where did tangent go? As x approaches pi over 2, it just keeps going up, up, and up. And before you know it, it starts to come down from under your feet and comes down from negative infinity, quickly going up to 0, and then going up to the sky again to pi, when x is 3 pi over 2, it goes up to infinity, undefined, and comes back again. So here, the period is actually pi, okay? And the fundamental region is defined this way here. And so, oh, by the way, when we define inverse functions, we talk about inverse functions later in this chapter, but we have to have a one-to-one function. So we have to restrict domains in a different ways. Okay, now I would like to do maybe one or two, maybe two transformation problems. Okay, so let's say y is equal to 3 cosine of x or something like that, right? Maybe add 2. Okay, so how do you do that? Well, this requires you to do two things. First, you amplify it so that the amplitude is going to be 3 times as big, which is going to be 3, and then you shift the graph to up by 2 units. All right, so let me draw my plane, and then we'll go from there. Okay, I have 2 questions here, graphing questions. Let's graph this function 3 cosine x plus 2. So you start with the original function. Let's say here the original function, you start at 1, and if this is pi and this is 2 pi, it goes down like this, -1, 0. Okay, again, the more familiar you are with the graph of the original function or mother function or the parent function, in this case, the cosine of x, the easier and the quicker you can graph these transformed functions. 3 cosine of x, basically you amplify it to 3. So 0 times 3 is of course 0. So it goes down like this. Maybe I should draw in another light color. All right. Nice thing about what's very nice about using a device like this, a tablet device, is that you have basically infinite collection of colors, right? So this is, again, I'm just sticking to one cycle, right? And later we can extend it if you need to. What I have drawn in blue is the 3 cosine of x. So remember, where it used to be the value of cosine of pi was -1, now it's -3. Okay, it's just amplified. It's stretched horizontally in a technical term. All right, now we are ready to graph this. Let's use blue for the final graph. The second and the final transformation is adding 2 to the y value, which will of course shift the graph up by 2. So instead of 3, it starts at 5. Okay, now it's really hard to draw this if you don't have any other helping lines. So I suggest you draw a little helping line, because you're shifting your y values by 2, moving 2 units up. Here is this line, y is equal to 2. This becomes our center line at this point, right? And so now this is 3 up here, which is 5, and then goes down, and it's going to hit right this point, which is what? Pi over 2, comma 2, right? And instead of this point, which is -3, you add 2 to it, that's -1, or 1, 2, 3 units down from that center line. And so this is what you get, and it goes back to 0, which is now 2, and then goes back to 3 units above that center line, which is 5. So this is my transformed graph, which is y is 3 cosine of x plus 2. Now, of course, this is not the only thing, right? You can keep expanding this. Let's see, you can just keep going like this, and then goes down to this point, and then goes here, and so on. If you have graphing paper, as I do, it's much easier, of course, right? But you should be able to do this kind of thing here, right? So that is what you can do if you are equipped with these skills called transformational techniques. All right, now the second one is slightly more difficult, mainly because the period changes. Here, the period is still 2 pi. Okay, so that's no problem. Here, the starting and ending point will change. And the way to do this, okay, and I think this is the the best of, or the easiest of all the methods introduced in various textbooks. I have seen many textbooks on trigonometry and pre-calculus. See, the thing is, sine and cosine function, you know how it behaves from 0 to 2 pi, right? So if the argument, which is now this, is 0 to 2 pi, let's set this equal to 0 first, and let's set this equal to 2 pi. Okay, because everything that happens in the typical sine curve, starting at 0, going up to 1, down to 0, going down to -1, and getting back to 0. Maybe I should draw this like this, going from 0 up to 1, down to 0, going to -1, up to 0. This whole period, or the cycle, happens between this and this, right? Well, let's find the x value of the starting point and the x value of the ending point. So this will give you 2x is negative pi over 2, x is negative pi over 4. So you can see, yeah, negative pi over 4 should be the starting point of this. For this one, if you subtract, okay, so let's say 2 pi, maybe I need a little more space here. 2x is equal to 2 pi minus pi over 2. This is 4 pi over 2 minus pi over 2. That's 3 pi over 2. So x is going to be 3 pi over 4. All right, so what do we just figure out? Let's call this negative pi over 4. And so that's 0. That's pi over 4. This is pi over 2. And this is 3 pi over 2. What we have discovered, 3 pi over 4. Okay. What we have discovered is between this point and this point, the standard wave of the sine curve is going to happen. So at this point, it's going to move up. Move up to 1. Maybe I use blue again. From 0, I have 1, 2, 3, 4, like 4. So think of this as I should have mentioned this. I think of sine, okay, you have 0 to 2 pi, right? Once you have this fundamental interval, I think of dividing this into 4 seasons, or like 4 quarters of the year. 4 seasons, spring, summer, fall, and winter. It's sort of nice and romantic, maybe not in California. But anyway, so if you go in the first quarter, the sine function goes from 0 to 1. Okay, and in second quarter it goes from 1 to 0, and then down to -1 and 0 again. So think of those 4 key points. It starts at 0, goes to 1, goes down to 0, goes to -1, and goes to 0. Okay, that is the complete cycle, which is the fundamental region, the fundamental domain of this particular problem. Is this interval, okay? Everything that happened, the complete cycle of the sine function happens between this point and this point, okay? Now, of course, you can extend it much more, and as long as you want to, if you want to continue doing this, okay? But again, this is, maybe not so simple, but it is something that you can do, and you can practice doing your homework and other extra exercises. All right, the last thing we want to do before leaving 1.3 is to talk about trig equations. How do you solve trigonometric equations? All right, it's not simply just applying your inverse functions, which is what some students want to do. The inverse functions will only give you one solution, okay, which is why it's a problem. Okay, so I'm going to give you just a couple of examples, and then for the rest of these, I will want you to struggle with your exercises you're assigned to, and make sure you learn how to solve trigonometric equations correctly. Okay, this particular skill becomes very crucial at various stages of calculus, and so make sure you learn this. Right, as I said before, many students struggle with calculus because they did not learn their trigonometry well. Okay, so by the way, when we say solve a trig equation, that means find all solutions, not just one. Okay, And you'd better be confident that you have found all solutions and didn't miss 2 or 3 or infinitely many. Okay, now this seems really simple, right? Because sine of theta is equal to 1. After all, the sine of an angle, if it's equal to 1, has to be over here. So the angle has to be pi over 2. Great, right? And in fact, if you take the inverse sine of 1, you will get pi over 2. Yay, you got the answer. Well, that's not all the answers. In fact, that's only one answer, right? Because if you add pi over 2 to 2 pi or 4 pi or 100 pi or subtract 2,000 pi's, 2,000 pi, you still get this point. So those are all solutions. All right, so what do you have to do? Well, you have to say, and by the way, on the unit circle, this is indeed the only place where the y-coordinate, the sine of theta, is equal to 1. So this is the only point on the unit circle. We just have to represent that point in all possible ways of theta. So theta is pi over 2. Now you can go 2 pi or 4 pi or negative 2 pi or negative 4 pi. So the way we do that is to say negative plus 2k pi, where k is an integer. You don't have to say positive or negative because integers include a positive and negative. Okay, so this is the complete answer. How many answers are there? Well, infinitely many. The one for each, integer. And so you want to provide the infinitely many solutions. And these are all the solutions because any other theta will give you points other than this particular point on the top of the unit circle, and therefore the sine is not going to be 1. All right, so this is the first question. The second question is a little more complicated. Let's solve this. 2 cosine of 4 theta is equal to 1. Okay, again, find all theta that satisfy this equation. You may want to pause this video at this point and see if you can solve this to find all solutions, theta that satisfy this equation, and see if you get this right by comparing your answer or your answers with mine, which I will show you in a moment. Okay, so feel free to pause this, try to work on this, and when you think you get the answer, come back to that. Ready, set, go. All right, so I hope you have figured out the first thing you do is divide both sides by 2. You have to kind of work your way from out toward the inside. So you divide this. So cosine of 4 theta is 1 over 2. Now we can divide both sides, right? So cosine of theta is 1 over 8 by dividing both sides by 4. No, you can't do that because cosine, again, is not linear. You can't move this 4 to the front. Okay? So all you can do is to say 4 theta is somewhere in this unit circle. Anytime you try to solve a trig equation, I highly, highly recommend. If I could, I would require you to think of the unit circle and pinpoint the answers or the answers, okay, in terms of the points on the unit circle. Where on this unit circle is a cosine? Forget the fact that this is 4 theta. Just think of this as some angle. Okay, cosine of something is equal to 1/2. Which point or points are we talking about? Okay, so 1, remember the cosine is the x value. So 1 is here, this is where 1/2 is. And the other is here. You have 2 points and exactly 2 points on the unit circle where the cosine of the angle is 1/2. One happens to be pi over 3, and the other is negative pi over 3, or you could say it's 5 pi over 3. Okay, these are the only 2 points where the cosine of the angle is 1/2. Okay, so that is what 4 theta is. 4 theta is either pi over 3 plus 2k pi, right? Because you can keep going around and around and around, or 5 pi over 3 plus 2k pi. Okay, so how do you find theta? Well, now you can divide everything by 4. So it's pi over 12 plus, now remember, if you divide this by 4, you get k over 2 pi, or 5 pi over 12 plus k over 2 pi. And we have found all of the solutions. Okay, now how do you know it's all of the solutions? Well, because we have identified every possible way to write these angles where the angle corresponds to either this point or this point in the unit circle. And those are the only points on the unit circle where the x coordinate is equal to 1/2, right? So this is how you solve that. Don't use the inverse cosine or inverse sine functions, because they will give you restricted. Remember, the inverse cosine and inverse sines are, and inverse trig functions have restricted domains, right? So they will only give you a partial solution. And if you do this, by the way, you are not going to get a lot of credit, because you have found one. What percentage of all solutions did you find? One out of infinitely many. That's like 0%, right? So you will get some points, I'm sure, but not much of partial credit. Make sure you know how to solve these trig equations, meaning find all possible solutions. And the way to do that is to practice, and practice some more. Okay, so that is section 1.3. Have a wonderful day.